Very good evening to all of you students. Okay, today we will be going for the experiment number 4, that is determination of friction head loss in a pipe flow. Uh, the structure of this talk will be similar as we did in case of the experiment number 3. There will be two parts. First of all, we will go for the theoretical details. We will go for a PPT. In the PPT, we'll understand the experiment to the fullest details, so that you will have a virtual feeling of the experiment in details. Then we'll go to lab and we'll see that how the experiment can be conducted. Okay, so coming to the first part of the talk, um, introduction. Aim of the experiment to determine frictional losses in fluid flowing through pipes. Indirectly speaking, we are basically interested to find out the friction loss factor, which is also called as the Dairy's frictional coefficient factor. Um, so for that, the apparatus required, the apparatus required for carrying out this experiment are the pipe frictional loss determination setup, or the pipe frictional loss determination experimental setup shown below, and a stopwatch. So this is the setup of what it looks like in the fluid machine laboratory in Department of Mechanical Engineering, where the experiment is basically being conducted. So different parts or different components of this experimental setup has been shown below. You can see one by one. First is a water reservoir, which is the source of water from which the water is being extracted or is being driven out of a pump and is being circulated throughout the system. So there is a water reservoir, uh, the first component. The second component is a pump for water circulation. There is nothing to explain much about that. You have already seen in case of the Bernoulli's theorem apparatus, you have got similar kind of components, one water reservoir and a pump, which helps to circulate the water throughout the circuit. Now the third point is a water collecting tank for experimental determination of discharge. Remember, in most of the, at least, in fact, I can say that in almost all the um, experimental setups or the experiments that will be conducted in fluid mechanics laboratory, you will have to find out discharge Q as a part of the experiment everywhere. Bernoulli's theorem apparatus also, you have found out the discharge, you have found out the value of the discharge. Here also you will be finding out the value of discharge. Similarly, in venturimeter experiment, and also there is one more experiment to follow. That is coefficient of discharge, coefficient of contraction. That experiment also, experiment 1 and 2. There also you will be finding out the discharge experimentally. So this is for discharge. How you are calculating discharge? You are calculating discharge that you have got a collecting tank. You allow the water to get collected in that tank. The cross-sectional area of the tank is known to you. So how much time is being taken for filling that tank up to certain height? That height you fix as per your convenience, maybe 10 centimeters, maybe 15 centimeters. That's as per your convenience, and the cross-section is known to you. So, and you calculate the time required for that through a stopwatch. Okay, this stopwatch I've shown it here. So you need the stopwatch for measuring the time taken to fill up that discharge or the water collecting tank or the discharge tank to a specific height. So that height is known to you, cross-section area is known to you. Multiply that height with the cross-section area. That will give the volume of water collected divided by the time taken to fill that. So the volume divided by time will give the discharge. Fine. Okay. Next is this is a view. Here I have tried to show you this portion basically. This portion. You see, this is the top view of that. You see that here the water is going and it is being bifurcating into four sections. So you have got 4 different pipes here. Okay, so the first one, this one is a copper pipe of diameter 16.6 millimeter. The second pipe was a aluminum pipe of diameter 17 centimeter, and the third pipe is a galvanized iron pipe, GI pipe of diameter 17 millimeter, and the fourth pipe is also a GI pipe of diameter 22 millimeter. So I call these two GI pipes to be GI1 and GI2. And all these diameters are actually the inner diameter. Okay. So these are the different four different pipes which are considered in this experiment, and we're interested to find out the frictional loss in this in these four different pipes. So as you can see that the pipes are of different cross-sectional area, and they're also different material. So we'll see that what is the effect of this uh, material and also the inner diameter on the frictional loss. So that will be revealed through this experiment. So as a whole, I can say that this is the experimental setup, and this experimental setup is uh, having four different types of pipes being considered. This is in a screen. These four pipes will be considered. Fine. Uh, okay. This is the piezometer is being used to indicate the loss of pressure head. We have already seen in case of in case of the bondless tube experiment that how do you find out the the loss of pressure head through these piezometers. There's no confusion about that. Okay. Uh, then you are having one more thing here. Yes. This is the distance L. Actually, all of these pipes, you could see, all these pipes are having two distinct points. This is point one, this is point two. Okay, this is point one, which is point two. So every pipe is having two different points from which the piezometers are being connected to know the difference in the pressure head. So, so the length between or the distance between these 2 points, one and two, which is being considered for each individual pipe for finding out the losses. That L is same for all the four pipes. So this L is equal to approximately 1 meter. Okay, fine. So I think this is all about the experimental setup. Yes, there is no doubt about that. Anything else I would like to tell you here? Yes, I don't think so. It is fine. So this is all about the experimental setup, the different components of the experimental setup, and that shown the different pipes being used, their diameters, and I said that the length is remaining, the length between the distance between the 2 points where you want to find out the pressure head loss is remaining constant, is 1 meter, is one for all, it's same for all. I said how to find out discharge, how to calculate discharge, how to measure discharge experimentally, which is a common phenomena for all the experiments to be conducted in this laboratory. And it's all about the aim of the experiment apparatus required. Now coming to the theoretical background. Actually, before coming to this experiment, I expect that in fluid mechanics theory, you must have read about how to calculate the frictional losses in case of a flowing through a pipe. Um, because of the whole purpose of the experiment, the whole purpose of the experiment is to verify this theory or the theoretical equations for the frictional losses experimentally. So although it might have covered, so I hope it might have covered. In spite of that, here I'd like to give you a small description about how this frictional losses are being calculated theoretically. So this is a theoretical background. So let's consider a pipe of uniform cross section A through which an incompressible fluid uh, is flowing at a steady state with a velocity v. We're interested to find out the drop in the pressure head at the 2 points separated through distance L. This is the figure. Yeah. This is a pipe of uniform area of cross section. Of course, as it is of uniform area of cross section, the 2 point, this is the point one, this is the cross section one and cross section two. Of course, the area of cross section will be same. A1 is equal to A2 is equal to A. The velocity will also be same as per equation of continuity because the area cross section is same and it is a steady flow, incompressible flow. So the velocity will also be same. V1 is equal to V2 is equal to V. Okay. Let the pressure at this point be P1, let the pressure at the point be P2. Always the pressure is normal to the cross section. So P1 and P2 are the pressures. This red arrows are indicating the forces F1 and F2. Okay, so the force will of course become how much? Pressure P1 into cross section area will be the force at this cross section. So this is force at this cross section. This is the force at this cross section. Now what is this Fr? Fr is your frictional resistance. That is your frictional resistance that is acting opposite to the direction of motion. So we're interested to find out this particular thing. Okay, Fr. Okay, L is the distance between these 2 points. So applying Bernoulli's theorem to the pipe flow at the 2 points 1 and 2, I can write it like this. this P1 by, just mean P1 by rho g plus V1 square by 2g plus Y1 is equal to P2 by rho g V2 square by 2g Y2 plus HF. HF is the head loss. You know that. Head loss. So both these points 1 and 2 are at the same datum level. So Y1 is equal to Y2. And as you see, the velocity is also same. V1 is equal to V2 is equal to V. So V1 square by 2g, V2 square by 2g will also cancel out. So ultimately, I'll be leading to this equation. P1 minus P2 by rho g is equal to HF. Okay, the HF is the loss of loss of the drop of pressure head is HF. Let the flow through the pipe be let the flow through the pipe be a flow such that it can be assumed that friction resistance varies frictional resistance varies linearly with respect to the velocity square. Okay, so I'm assuming it is a standard assumption being taken during this derivation that the frictional resistance is approximately um, um, proportional to the velocity square. So accordingly, let the frictional resistance per unit volume per unit velocity be given by F dash. Let the frictional resistance acting on the flow per unit area per unit velocity be F dash. Then the total friction resistance per unit velocity, not per unit velocity, the total friction resistance, just a minute, yes, no, you can just correct it. Total friction resistance, this per unit area won't be there. Total friction resistance will be given by Fr is equal to how much? You'll be multiplying the total cross section area pi d into L, where d is the diameter of this pipe, pi d into L is the length into V square. Okay. Now, if I apply Newton's second law, total force acting on the body is equal to mass into acceleration. It's a steady flow, so acceleration will be zero. Velocity at both the ends is same, v. So there won't be any acceleration. So I can write it like this: F1 minus F2 plus Fr is equal to mass into acceleration. So that term becomes zero. So F1 minus F2 plus F1 minus of F2 plus Fr is equal to zero. So that I can make it like this: P1 A1 minus P2 A2 minus Fr is equal to zero. So it leads to this equation. A is constant for both of them. So P1 minus P2 is equal to Fr by A, where Fr is the frictional resistance that is being calculated like this: F dash into pi d into V square divided by A is equal to pi d square by 4. So it leads to this equation: 4 F dash into L V square by D. So here, I will come to this through this substitution. I can substitute like this: F dash by rho is equal to Cf by 2. Cf is the coefficient of friction. Cf is the coefficient of friction. So if I replace F dash by rho by Cf by 2, then I'll be having this equation. Now this 4 into Cf, 4 times the coefficient of friction, is called as F, which is also known as the Derry's friction factor. So ultimately, I'll be leading to this equation: HF is equal to FLV square divided by 2GD. So this is my final expression, or is also called as Derry-Weisbach equation. It's a common equation in terms of fluid mechanics. It might have been derived also in the theory, but it was just a repetition. I thought that it would be better if I tell you the theoretical background before I move to the experimental details about experimental verification of this equation. So we are finally concerned with this particular equation: HF is equal to FLV square by 2GD, where FHF indicates the pressure drop, the pressure head drop, P1 minus P2 divided by rho g at any 2 points separated by distance capital L, and this L is same for all the pipes. So HF is equal to FLV square by 2GD, where F is equal to friction factor. The coefficient is the Darry's friction factor. L is the length, which is I told to be 1 meter for both for all the pipes. V is the velocity. Capital D is the diameter of the pipe. So this is the theoretical background. I think it is clear that what is the theoretical basis of this equation, what we're basically trying to verify in this experiment. So this is theoretical background. Now coming to the next part, here we'll be seeing the procedure. So procedure, let me directly tell you that our purpose is this equation: HF is equal to FLV square by 2GD, and we want to calculate this F. F is my friction factor, or my Darry's friction factor. F is equal to HF 2GD divided by LV square. So if you look at this equation, you see, I'll just discuss the terms one by one. First term is L, distance between the 2 points. I have already shown there are 4 pipes. Each pipe, there is a copper pipe, there is an aluminum pipe, there is a GI, there are 2 GI pipes. For each of the pipes, there are 2 points about which you are trying to find out the pressure drop. So that length is that L between these 2 points is nothing but to L. That L is same for all the pipes. That's why L is equal to 1 meters. It's constant for all. It's a known data. So nothing to worry about, nothing to be worried about this particular data. It is same for all. L is equal to 1 meters. Now, coming to next data, D. D is the diameter of the pipe. I've shown there are total 4 pipes being taken in this experiment. You are taking 4 different types of 4 different diameters, which are already mentioned over here. You could see that diameter D, capital D stands for diameter D of the different pipes considered. They are copper pipe of 16.6 millimeter diameter, aluminum of 17 millimeter diameter, GI1 pipe, GI1 is 22 millimeter diameter and GI2 is 17 millimeter diameter. All these diameters are in fact the internal diameters, ID. Fine. So this is also known parameter, nothing to be worried about that. So I just want to tell you that what exactly is to be, what are the data that are to be collected from the experiment. हम लोग experiment किस लिए करेंगे? What exactly is to be taken or what exact reading is to be taken out of the experiment. That is what I want to tell you. So D is known factor, L is also known. So that has nothing to do with the experiment. Now coming to the next point is V. V is the velocity of flow. V is the velocity of the flow. How will we finding out the velocity of the flow? That you have to find out experimentally. So that velocity of the flow is equal to discharge by cross-section area. So discharge you'll be finding out from the experiment. I've already told you that there is a discharge tank. So you will be making suppose how will you finding out the discharge? How will you finding out the velocity? Actually, velocity is to be found out in that particular pipe in which you are trying to find out the loss. There are 4 pipes. So suppose you want to find out the loss in the pipe number in the copper pipe. So what will do? You will try to you will now you will make the fluid to flow through the copper pipe. Now as the copper pipe is as the fluid is flowing through the copper pipe, now you will try to know what is the discharge for this particular copper pipe. That is why every pipe, I'll show you in the experimental setup, you'll see that all these 4 pipes are having all the 4 pipes are having one input end, one output end. At the output end, you are having a discharge, some discharge pipes. So the pipe in which you want to find out, or measure the discharge pipe connected to that particular pipe is being connected or is being connected to the discharge tank. Okay. बाकी जो थी सपोज कॉपर पाइप में मुझे इफ आई वांट टू फाइंड आउट द डिस्चार्ज टू द कॉपर पाइप, तो कॉपर पाइप का एंड से जो डिस्चार्ज पाइप निकल रहा होगा दैट इज टू बी कनेक्टेड टू द कलेक्टिंग टैंक एंड द रेस्ट 3 पाइप्स द GI1 GI2 एल्यूमिनियम पाइप के जो डिस्चार्ज पाइप्स है दैट विल बी डायरेक्टली कनेक्टेड टू द टैंक, दैट विल नॉट बी गोइंग टू द डिस्चार्ज टैंक. व्हाट आई वांट टू से इज दैट you in the pipe in which the discharge is to be calculated or measured, the discharge pipe or discharge pipe connected to that particular pipe will be connected to the collecting tank, so that you can see that for a particular height to be filled up, for is a time taken. So you multiply cross sectional area into that height and you divide that by the time taken, you will get the discharge in that particular pipe. Okay, once you got the discharge in that particular pipe Q, then you divide, already the diameter is known to you, the pipe diameter is known to you, so pi d square by 4 will be giving you the cross sectional area. So you divide that Q divided by the cross sectional area will be giving you the velocity in that particular pipe. Fine. So that is how you will be finding out the velocity, the velocity of flow through a particular pipe. Now the next is HF. This HF will be coming through the piezometric reading. I've already shown you in the experimental setup that every pipe is having 2 points. From these 2 points, you're having the piezometric wires are going over there. And once there'll be steady flow, you could see that there'll be a difference in the piezometric heads. There'll be, because at these 2 points, if you see the piezometer carefully, there'll be a difference in the piezometric head. So that difference in piezometric head will be your HF, which will be coming directly over here. I'll be showing you in the experimental part that how it is being experimentally being taken. So this is all about the procedure. The whole purpose of the experiment is to just calculate 2 things. You have to calculate what? The HF, that is the loss of pressure head, which will be coming from the piezometric heads or the piezometric readings. And the second thing is the velocity. For velocity, you need to just calculate the discharge because area cross section is known to you. Fine. So, so as you have to calculate the frictional loss for all the 4 pipes, so accordingly the table I will just showing you one table. So that table you have to repeat for each individual. Which I'll just show you one sample calculation how it is to be done, and that the table what I'm showing you, that the same table can be repeated for different discharges. You can have different discharge, and for each discharge you can calculate. You can have a table like this. So let me show you a sample calculation for a particular discharge, say Q1. This table has been taken. This have been taken from one of your seniors. You could see these are the pipes. Actually, there are 4 pipes, but I don't know, he might have used a different setup. I don't know. For the present setup, what he's having in the laboratory, it is having 4 pipes only. So GI pipe, aluminum pipe, copper pipe, and GI2 pipe. You could see the head drops. These head drops are nothing but this HF, what he's calculating for each individual pipe. And here you could see this is what this is rate inside. This is the discharge. This is a discharge. Okay, meter cube per second is a discharge. That means Q. Okay, so for each pipe he's just taking two data. You could see. Suppose GI pipe, the pressure drop is equal to say 25 millimeters, and the discharge he calculated to be 5.8 × 10⁻⁵ meter cube per second. Okay. Similarly, for the other pipes, he has calculated it. Once he has got the discharges, now he has the cross-sectional areas. He will divide with that. Then he will get the velocity. HF is known to him. L is equal to constant 1 meters. Diameter of the pipe is known. So accordingly, he will get the corresponding friction factor. Fine. So this table, whatever he has done for a particular discharge, he may repeat it for different other discharges, and he can have different tabulations to verify the same fact. Okay. Finally, conclusion. This formula is based upon this assumption that the frictional coefficient is proportional to the length of the pipe, and also it is directly proportional to square root of the velocity. And friction coefficient is also inversely proportional to the pipe diameter. These are known facts. So these are few conclusions are mentioned. I think this is all about the experiment and the theoretical details about the experimental setup, different components, the theoretical background, and the procedure to conduct the experiment. I think this covers all. And in the next part, we'll be seeing in the laboratory how we will be conducting the experiment practically in the laboratory. Thank you.